welcome to today's webinar. Before we begin, we wanted to cover a few housekeeping items. For any common technical issues, please refer to the Help widget located at the bottom of your screen. If you have any questions during the webcast, you can submit them through the Q&A widget. Questions will be answered immediately following the presentation. Any resources and links provided from today's presentation can be found in the resource list. An on-demand version of the webcast will be available approximately 1 day after the webcast and can be accessed using the same audience link that was sent to you earlier.
All right, so welcome everyone to today's webinar on reinforcement learning. Very excited to have you here. Reinforcement learning is a fantastic research area that is seeing a lot of great progress. But before we get into the details of what reinforcement learning is all about, I want to say just a few words about myself. In the top corner there, you see a snapshot of my team, which together with me works usually in Cambridge in England in this beautiful building that you see here. And my team and I share the conviction that within the gaming space, reinforcement learning will make a big difference. And so a lot of the research that we do at MSR in Cambridge within the gaming and AI organization is looking at reinforcement learning with potential applications in the video game space. One of the projects that my team has developed is Project Malmo, which is an AI experimentation platform on top of the game Minecraft. And so it unlocks Minecraft as an experimentation platform for RL and other artificial intelligence research. But let's dive right in. Reinforcement learning can be very briefly defined as a principled approach to decision-making and learning under uncertainty. And this type of approach, decision-making under uncertainty, is something that occurs in a wide range of everyday situations as well as a wide range of applications. So if you think about all the choices that you need to make every day, a lot of those can be framed as a reinforcement learning problem. For example, where to go for dinner, when to study and when to enjoy leisure time, what course of study to take, etc. All of those are decisions where the outcome is uncertain and where you need to understand how to make those decisions under this uncertain situations. But let's take a more concrete example here in the video game of Minecraft. We are here looking at the game Minecraft from the point of view of an agent that observes a screen here from a first-person perspective. So we model this agent as being directly embedded in the game and experiencing the game from a first-person perspective. The agent needs to interact with its environment, so we model this as taking actions in this environment. For example, here the agent might decide to move forward towards the zombie that it's facing. We also typically assume that there is a reward signal that the agent can learn from. In this case, nothing exciting happened, so we can assume that the agent got a reward signal of 0. And then this continues, and you can think of this as a cycle where the agent observes the next observation, it takes an action. So for example, here it might issue the attack command, it receives some reward signal, in this case again of 0, and it obtains the next state. So we can play this forward. And so here we come to an example where the agent observed a non-zero reward signal. And we can think of reinforcement learning as this principled approach that needs to understand, or that allows the agent to learn what the consequences of its actions are in complex environments, and then given that understanding of the consequences of its actions, how to continue to interact with an environment in such a way that it maximizes its own reward, its own long-term reward. And so one interesting observation here is that even though this reward of +1 in this case was closely associated with the kind of attack action that we think had a kind of played a big influence on getting this reward because we actually hit the zombie, in many cases the reward that is associated with various actions the agent has taken may in fact be delayed. So it might take a very long time for the consequences of the agent's actions to actually pan out. And so we run into this problem of having to understand how to learn consequences from that stream of data of the agent continuously interacting with its environment. So even in this simple example, we can see some of the key challenges that we face when we try to come up with principled approaches to solve reinforcement learning problem formulations. The first one I already mentioned is about how to attribute consequences to the sequence of previous actions and states that the agent has encountered. So for example, here we may want to attribute quite a big contribution to this attack action in this specific situation, but maybe moving forward so that the agent is placed in the right position to attack also played a role in getting this positive reward. And so how should the credit for those various choices be distributed over those action sequences? And most importantly, how should this change the agent's behavior policy so that it's able to get higher reward in the future? Now, this problem is typically called the credit assignment problem, and it's one of the key challenges in reinforcement learning. There are two other key challenges. Typically, we want reinforcement learning algorithms to interact in domains that are complex. So, for example, here, the agent is experiencing its world from this first-person perspective where it observes high-dimensional pixel images. So how should it interpret those observations in such a way that, again, allows it to perform credit assignment even in situations where observations are high-dimensional? This is typically called the function approximation problem. And finally, we need to understand how the agent should interact with the world. So what kind of behavior it should actually perform given what it has already learned and given that it wants to continue to learn about the consequences of its actions. This is the third key challenge in reinforcement learning, and it's also referred to as the problem of balancing exploration and exploitation. So briefly, we want to ensure that the agent continues to explore alternative courses of action so that it can learn about their consequences, while also making sure that it exploits what it has already learned so that it can benefit from that knowledge and get high reward as it is interacting with the environment. Now, this relatively straightforward problem formulation has a huge number of potential and actual applications in the real world. So just to mention a few of those, in a healthcare setting, we might formulate the problem of deciding what treatment to prescribe to a patient as a reinforcement learning problem, where, again, the consequences of a particular course of treatment are uncertain given the current knowledge about the patient's symptoms. In a science scenario or discovery scenario, we can model the problem of deciding what experiments to run in what order in order to continue to learn as much as possible. We can imagine transport settings where, for example, we might want to time signaling in complex transport settings. Or, as already mentioned, in gaming, there is a wide host of applications, including to understand how games could be more engaging, could create new experiences to their players. In the lecture today, we will be looking at, initially in the first lecture, some of the foundations of reinforcement learning, starting very importantly from an understanding of how to formalize reinforcement learning in such a way that we can derive principled approaches to this problem. We'll be looking at a first set of such approaches, which are based on the Bellman optimality equations, and the approach we'll be looking at is QLearning, and we'll come back to the problem of balancing exploration and exploitation. Finally, in this lecture, I want to conclude by taking a look at what the states, rewards, and actions typically are for an agent, and just make clear that those are very important design choices that need to be well understood when someone wants to apply reinforcement learning in practice. I'll take a short break here just to see if there's any questions. Do we have any questions so far? No, if someone still wants to sit in the front, there's still some space here. All right, all good so far, so let's continue. Starting with formalizing reinforcement learning, I want to just be clear that this formalism is not just a way of putting nice pictures on the slide here, but it's really important because it lets us very clearly specify our assumptions about how an agent interacts with an environment in this particular setting. It allows us to make simplifying assumptions, and those simplifying assumptions are really crucial for then deriving efficient algorithms for solving reinforcement learning problems. So as we already saw, in reinforcement learning, an agent is modeled to interact with an environment. We typically model this agent as having the goal to learn an optimal behavior policy. And the policy is typically some distributions over actions given the current state observation. We typically assume that the environment that the agent is interacting with is initially unknown. And this is a very important assumption because it makes the problem a lot harder. If we had a perfect model of the environment, we could reduce the problem to a planning problem where we can work out all the consequences of the agent actions without actually interacting with the environment. We already saw the kind of basic framework of how the agent interacts with the environment. We assume that agents interact by sending actions from some action space A, and in return, the agent observes some reward signal, which is typically a single scalar, as well as a state observation in some observation or state space S. To complete the formalization here, the agent is assumed to act with a policy pi that maps states to actions. So it's a probability distribution over actions conditioned on the current state observation. And we model the environment as having the following dynamics and reward function. Again, importantly, those are unknown, but we assume that crucially, the transition dynamics that govern the environment tell us that the next state that the agent will find itself in will be a function only of the previous state and the action taken at the previous time step, and that the reward function, again, is a function of, again, the previous state and the previous action. And this assumption is very important. It's the one crucial simplifying assumption that led to a lot of progress in reinforcement learning over the past decades. So let's look at this assumption in a little bit more detail. We can summarize the formalization that I just mentioned in the tuple shown here on the screen, which is typically called a Markov decision process. So it's a Markov decision process M, which is defined by the state space, the action space, the probability distribution over the transition of the environment, the reward function, as well as a discount factor gamma. Given this definition of a Markov decision process, we can write down the goal of our agent. I already informally stated that our goal is to develop an agent that takes actions that get the highest long-term cumulative reward. And here we can write down this quantity in more detail. We typically formalize this as the return GT. So it's the return that the agent can obtain from a time step T. And it's the infinite sum of rewards that the agent can collect at every time step. And this sequence of rewards is typically discounted by this discount factor gamma, which is typically a number that is less than 1, but typically very close to 1. And it captures the intuition that this potentially infinite interaction between an agent and the environment has some non-zero probability of stopping at every point in time. And so you can think of this discount factor as modeling the probability that the interaction between agent and environment will stop. And this makes it important for the agent to get to potential rewards sooner rather than later, because if rewards are very far in the future, there might be no time to actually collect those rewards. Now, the crucial assumption that I already alluded to here is the Markov property. And as you saw in the previous slide, the Markov property makes the simplifying assumption that the environment dynamics and reward function are purely a function of the previous state and action. This is simplifying the problem a lot because it means that whenever we work out an agent's policy, we only need to model the distribution over its actions given the state. We don't need to maintain the entire interaction history between the agent and environment, which allows us to develop much more sample efficient algorithm. This understanding of the Markov property and its importance to initially planning goes back to Richard Bellman. For example, his paper in 1957 already pointed out the importance of the simplifying assumption, and Bellman played a crucial role in deriving some of the initial understanding of how we can address complex decision-making problems, initially in the form of dynamic programming. And now a lot of the reinforcement learning approaches we use today go back to some of those initial ideas that were developed in this context of planning in the dynamic programming setting. Right, this concludes the formalization of reinforcement learning. Are there any questions up to this point? Yeah.
Problem. It's exactly the same as what we call general dynamic programming. Kind of, we use the dynamic programming to solve the planning problem.
That is exactly right. Yes, exactly. And there's an interesting story about why he picked the term dynamic programming. He wanted to not get anyone to notice that he was actually working on mathematics. So there's an interesting story there. Yeah.
The definition of states and the transition dynamics is done a priori.
So the definition of states is something that is under control of the person who applies reinforcement learning or who formulates a specific problem as a reinforcement learning problem. The transition dynamics are an assumption that we make about the environment. So when we apply, for example, what's called model-free reinforcement learning approaches, we don't explicitly model the transition dynamics. We just assume that the environment is governed by dynamics that are Markov or approximately Markov, which then gives us an insight on whether our approaches have any hope of actually working in that environment.
Even in the case of model-free, the states will need to be defined.
Yes, that's right. And so that would be a choice that is under the practitioner's control. And so the practitioner, or for example, someone working with a domain expert, would have to understand what, for example, state features the decisions rely on. And they would need to make sure that all the information necessary to make a decision in that particular domain kind of is captured in the state space. And that's, as you mentioned, that's an important aspect of formulating the problem as a reinforcement learning problem. In many situations, it actually is possible to make the problem fully observable, like we're assuming here, and using the Markov property. In some settings, that might not be possible, and then you're in a different formulation, which is called a partially observable Markov decision process. Where you need to smooth over the history, for example, but we won't be going into detail on that today. Oh, yeah.
So the Markov decision process you described is discrete, right? Is there like a continuous analog to this?
There's a lot of continuous analogs. So do you mean time discrete, or do you mean the state and action spaces?
So the state and action.
Right. So with function approximation, in general, we're not limited to discrete state and action spaces. And apart from the initial examples in the tabular setting, all the approaches I discussed will, in principle, generalize to a continuous state and action space. There's some caveats in the sense of continuous action spaces are usually a little harder to explore. We'll get into some of those details in the second lecture. But in principle, reinforcement learning as a problem formulation doesn't care whether the problem is discrete and continuous. And in fact, Bellman initially was focusing on continuous problems before people in the reinforcement learning community started to look more at the discrete equivalence.
There's the question, what about continuous time?
Say again?
What about continuous time?
Yes, in principle, it's possible to formulate it as a continuous time problem. It's harder to actually do the RL problem, right? So if you have something given in terms of differential equations, you can work out solutions in relatively simple cases. And so in the control theory community, those problems are quite common. Without additional assumptions, those are hard from an RL perspective. We can follow up offline, but it's not something that is currently looked at in the kind of mainstream RL literature. Yeah.
Is there any reason you chose Minecraft as your domain?
That's a really good question. Minecraft is a fascinating game because it's a meta game. And so one of my kind of long-term research goals is to develop RL agents that are able to learn lots and lots of tasks with relatively little additional data. And so Minecraft is a fantastic testbed for that because we can kind of get people to create essentially any number of tasks in there. It's something that players already do. They create mini games, they play with their friend. And so by tapping into that, we essentially have the whole richness of that environment as a playground for reinforcement learning agents. All right. Thanks for the fantastic questions discussion. I'll move forward with looking at Bellman optimality and Q-learning. So now that we've formalized reinforcement learning as, in this case, an instance of a Markov decision problem, we can look at approaches on how to actually solve this problem. The examples I'll be giving in this section are relying on Project Malmo. So here's just a quick overview. If you want to try some of the examples that I'll be showing, Project Malmo is an open source platform. It's available for free on GitHub. And so you can download this and try this out at home. The example that we're using to illustrate Q-learning is a Minecraft rendering of a classic reinforcement learning task called cliff walking. And within Project Malmo, this is the tutorial 6 if you want to follow along. Just a quick reminder, in this environment, we can see the agent with an environment that is initially assumed to be completely unknown to the agent. So the agent starts with no knowledge of what the various blocks mean in this environment, even though we can, of course, visually see what's going on there. The way the agent interacts with this environment is that in this case, we start from a tabular representation. So every block that we see that the agent can move to is modeled as a distinct state. And the agent has 4 actions available. So at every point in time, it can move north, south, east, and west. The reward structure, as you can imagine, is negative when the agent falls in lava, and the agent observes a positive reward when it navigates all the way to the goal. So our goal here is to have an agent that learns to navigate to this positive reward with as few samples as possible. We can actually illustrate this relatively simple example in the form of what is called a Q table. And in this tabular representation, we see a cell here for every block that the agent can navigate to in this environment. We also see that each block here has a little circle, and this circle indicates both the 4 actions that the agent has available at any point in time, as well as our current estimate of how good the given action is in that particular state. And we'll see in just a couple of minutes that this is called a state action value or Q value. So we'll come back to this concept very shortly. And we can see in this tabular representation here the current state of knowledge that the agent has so far. So we can see that it has some estimates of the quality of the actions that it can take in this area and that area, but large parts of the environment are still unknown, and it doesn't have any estimates of how good its actions are in those parts of the environment. Now, if we run an algorithm called Q-learning, given this current knowledge that the agent has, this is what we see. So as you can imagine, because the agent currently does not know what the consequences are of visiting those various state action pairs that we see here, it is prone to falling into lava and getting that negative experience of what it's like to fall in lava. Now, how can we get the agent to actually learn how to behave in this environment? As already mentioned, a crucial concept in this setting is the so-called Q value, or state action value, which is defined here. So our Q value under a given policy pi for the current state ST and the current action AT is defined as the expected long-term cumulative reward that the agent can obtain when taking action AT in this particular state ST. And based on the formulation of the agent's goal that we saw earlier, we can actually write this as this expectation under the current policy of the long-term discounted cumulative reward, just as we saw previously. Now, the key insight that Bellman actually contributed to the community when he was working on dynamic programming is that there is a recursive relationship hidden in this definition, and that we can actually make use of this recursive relationship in order to efficiently solve reinforcement learning problems. The recursion here is that the task of finding an optimal policy can be formulated as the task of finding the initial optimal action and then following some policy moving forward. And that is exactly the recursive relationship that he discovered. So we can move to this by first writing out this expectation here as the sum of the immediate next reward plus the discounted expected reward for the remainder of the sequence. So all we've done here is that we have taken apart this infinite sum, we have chopped off the very initial element, and then we have written this out as the sum of this element plus the remainder of the sequence. This can be just looked at visually here. This gives rise to a very important concept called backup, where the recursive relationship allows us to model the return from every state action pair as the sum of the immediate reward obtained plus the remainder of that sum. And we can calculate this remainder of the sum because we have an estimate, an initial estimate for all the state action pairs in our domain. So for example, going back to our Minecraft example, if we want to work out the value of the action AT in this particular state, we can take a step in this direction here, observe the one-step reward we get for that transition, and then back up to our estimate of the value of this follow-up state that we have at this point in time. And this is an approximate iteration which can actually be shown to converge to the correct Q values for a given domain. And initially that was shown by Bellman for the dynamic programming setting. So initially not yet for the reinforcement learning setting where an environment simulator might be unknown. So this is one of the kind of key insights in reinforcement learning, that this recursive relationship can be used to work out the values of all the state action pairs in a given domain. Bellman's book from 1957 does get into a lot of detail on this and really describes key insights that still form the foundation of reinforcement learning today. Now, how do we get from this recursive relationship to an actual practical algorithm that we can use to solve reinforcement learning problems, even when we don't have access to a reliable environment simulator? This kind of a set of effective algorithms, including QLearning, are based on an insight called temporal differences. Again, temporal differences are based on the recursive relationship that Bellman illustrated earlier. And we can look at the temporal difference error on the slide here. So if we look again at the Q value for given state ST and given action AT, and look again at this relationship, then we can rewrite or we can write a specific error called delta if we compare those two quantities. So if we imagine we are in a situation where we need to work out the values for all state action pairs, eventually this difference here should be precisely 0, because as we've shown previously, we can exactly write the Q value in terms of the sum of this immediate return plus the remainder of the reward sequence. Now, if we have an error, this quantity is called a temporal difference error, and a wide range of reinforcement learning algorithms actually relies on the fact of minimizing this temporal difference error all the way until the sequence of iterates has converged to an error of 0. A very effective algorithm for doing this is initially in the tabular setting was developed by Watkins, who was based in Cambridge in the UK. So it's a good place for reinforcement learning, and it has been since the 80s. And a sketch of the algorithm is shown here. So here we no longer assume access to a perfect simulator of an environment, and instead we really have an agent interact with the environment step by step. Briefly to go through this, for each episode we initialize our state space, and then from a given S we choose an action A using a policy that is derived from Q. Here's a brief note that an example of such a policy can be an epsilon greedy policy. This connects to this problem of exploration and exploitation that I mentioned earlier, and we will look into more detail of what possible alternatives are in just a few minutes. But for now, it's enough to say that an epsilon greedy strategy follows the maximum Q value most of the time, but has some non-zero probability of taking exploratory actions at every point in time, in order to make sure that the agent has probability 1 of visiting all state action pairs in the limit of interacting with the environment. So the agent has chosen an action, it takes this action and observes the reward and the next state. And then the update rule to the Q values follows exactly the recursive relationship that we have seen earlier. So we back up our updated estimate of the Q value by taking some learning rate alpha times our immediate reward plus the gamma discounted maximum Q value for the next state that we could find ourselves in. And as you remember the temporal difference error, this quantity exactly minimizes the temporal difference error on the state action pairs that the agent encounters. Not only did Watkins develop this algorithm, he and Peter Dayan were able to prove that QLearning is guaranteed to converge to the optimal policy in the discrete state action setting. And so this was a really important insight here. So let's look back at what QLearning looks like in Malmo. This is what happens after training the algorithm for about 10 minutes. And you can already see that at this point, we have a much, the agent has a much fuller understanding of the state action values in the given environment. We can now see that by following its current policy, it still takes some exploratory steps and doesn't take the shortest path to the goal, but it has found a safe passage to the goal and is able to achieve high reward on this task.
In this case, we call model 3.
Let's take a few minutes for questions. Sure. Mm-hmm.
It's a model 3 in this case, or we can consider that it's a model based because we're kind of building this model of the policy.
Mm-hmm. So the traditional definition of model 3 would be that this is a model 3 approach. This Q value representation that I'm showing here is something that I used to visualize the Q values, but the transition dynamics of what this actually means aren't actually known to the agent. It's something we can project into because we know the arrangement of blocks, but it's not knowledge that the agent would make use of. Yeah.
So in your game, the agent got the lava experience, right?
Yes,
so
exactly.
Is there a way to reduce the number of times the agent will experience the lava?
Mm-hmm. That's a great question.
Real-time consumers.
Right. This is really at the heart of what it means to make reinforcement learning more applicable in practice. Typically, in order to reduce the number of samples required for learning, means that we need to either make additional simplifying assumptions, or we need to provide some additional knowledge or some additional information. And that additional information could, for example, be an initial policy, maybe a demonstrated policy by an expert or by a baseline algorithm that we could take as a lower bound. That would be one way to inject kind of expert knowledge in order to allow for more sample efficient algorithms. We could make additional simplifying assumptions or structural assumptions about the transitions of the MDP, or basically anything we know about the environment can be formalized as constraint or some other form of knowledge that can make learning faster. Mm-hmm. Any other questions before we move on? Yes?
Sorry, this is off policy because when it is learning, it is not following a specific initialized policy for.
That's a really good question. So I haven't mentioned the on policy, off policy kind of distinction yet. QLearning is an off policy algorithm, and it's called that because what it learns about is the optimal policy, not the behavior policy that it follows. So as you recall, it follows what's called an epsilon greedy policy, but it actually learns the estimates for the optimal policy it could follow if it were to take the maximum value action at every state. Yeah.
So in this example, how do you define state? Is the state correspond to a grade in this?
Yes, in this particular one, in the kind of tabular formulation,
Right.
we assume that every cell is a.
But then I wonder, since your learning process happened only at the beginning part of the sum of states, it's not clear to me how would you extrapolate that to the states that you haven't seen.
That's a very good question, and it's exactly one of the limitations with this tabular formulation. In this tabular formulation, there's no way for the agent to use experience from, let's say, similar states to learn about the consequences of actions in other states. And this is where we need to move into QLearning with function approximation, which is an approach for generalizing to unseen states that are similar to what we've seen before.
So the example you showed is actually not what, actually use some technique you haven't talked about.
The example I showed does not generalize over states. So that's why, as your colleague mentioned,
the character can move ahead and avoid that and get the reward, right?
Yes.
So it must have used some technique you haven't yet covered, right?
So far, I've covered all of this. So we have used epsilon greedy exploration to work out the state action value of every single state action pair separately. And the agent in this case did not generalize over those. The only thing I've done is I've shortcut. I haven't shown you the entire 10-minute learning process, and I've jumped straight to the end. But under the hood, all that exploration kind of over the course of 10 minutes. Yes, exactly. I've only showed you the first 3 episodes, but yeah, imagine that this went on for, the agent died in lava a couple of thousand times before it got to this situation. Great question, yeah.
You mentioned that convergence is always possible in a discrete state space. Would the optimal solution always require brute force going through every permutation of every state action pair possible in your Q table, or is there optimizations possible to not have to force that?
So all the guarantees that I'm aware of assume that the agent can visit each state action pair infinitely often in the limit, and all those are convergence proofs in the limit of infinite data. As was mentioned before, you could, if you know something else about the domain, you may be able to derive an approach for a subset of MDPs or for the specific constraint problem you have. You may be able to get guarantees there, but those would be less general. And so then it would be you have to look on a case-by-case basis, what are your assumptions and what does that mean in terms of convergence guarantees, for example.
I have one more question. Was that in this specific domain, do you have an API for figuring out the state, or is this computer vision on top of that?
Yes, so within Project Malmo, we have the concept of observation handlers. And so with observation handlers, the experimenter can pick and choose in what way they want to expose states to the agent. So there's the tabular representation here. It could be vision, it could be the depth map. There's you can get chat from other agents, etc. So there's a lot of choice in terms of how the program is formulated in this particular point in time. Oh. Yeah.
So the notion of discounting, it feels like you're kind of limited to exponential discounting in the way the recurrence is set up.
Yeah.
And that feels like there's a form of bias. Is there any way to
Right. That's a really good question. So it is a recency bias. And so the kind of intuition there is that it's better to get rewards sooner rather than later. There is research on this. Martha White has looked at a more general form of discounting. She published on this in the last 2 years, so ICML on Europe's in the last 2 years. So there definitely are people thinking about this, but it's not something standard. It's something that is only coming up now. All right, let's move on. So, oops, let me get big here. So as you may have already noticed, with the tabular representation that we've seen before, the agent can learn very effectively in relatively small state action spaces, but there is a key limitation that the agent is not able to generalize to unseen state action pairs. And so with the tabular representation, it would need to visit all state action pairs in order to learn about the consequences of taking actions in those particular states. A type of approach that aims to get around this limitation is what's called QLearning with function approximation. And so the key idea there is that instead of building up the table of Q values explicitly for each state action pair, we learn a function approximator that approximates the state action values instead. The change from tabular QLearning to QLearning with function approximation is conceptually quite straightforward. And you can see that this relies, again, on the notion of a temporal difference error. We see exactly the temporal difference error that we formulated before, but now in a function approximation setting, we can use this temporal difference error as an objective where we need to minimize the loss. We minimize this temporal difference error by updating the parameters theta of our function approximator. And so you can, for example, imagine the function approximator to be either a linear function of our state action features or, for example, a deep neural network. And so we would here have a very straightforward recipe of what we need to do to update the parameter vector of our linear function approximator or the parameters of our deep neural network in order to minimize this particular error. In terms of practical implementations, minimizing this error is as simple as using a current deep learning framework and actually minimizing this objective using stochastic gradient descent. I will highlight in just a few moments that even though conceptually simple, it took quite a lot of research to understand how to actually implement this and get this to work well in practice took quite a few insights, because what we're doing here is essentially taking reinforcement learning, which is a highly non-stationary problem. The data under which we minimize this objective changes over time as our exploration policy changes. And this leads to instabilities compared to if we were to do this in a supervised learning setting where the set of data that we learn from is fixed ahead of time. But before we kind of take a closer look at some of the pitfalls and solutions there, let's just look at an example of where we translate our earlier Minecraft domain into a problem where we actually learn with QLearning and function approximation. We see our Minecraft agent here in a similar maze environment. In this one here, we actually trained this agent to navigate arbitrary mazes. So even though the location of lava in this case is fixed, we can vary this over the course of the environment. What you see here in the top left corner is the actual observation that the agent receives. So this, in this case, are the 4 previous frames that the agent would observe from a first-person perspective. And we can see here in this corner the current Q value estimates of the agent, where we see a very large negative estimate for the action of moving forward, which is a very sensible estimate given that the agent is actually facing a pit of lava at this point in time. Running the agent policy, we can see how it's moving around the environment and how its Q values are changing as it navigates the environment. You can see here that whenever it faces a clear path, the Q values are all positive, and whenever it faces lava, it is able to generalize and very effectively model that there is a dangerous situation it shouldn't get into. So I want to just briefly summarize what we've seen so far. We have discussed reinforcement learning as a principled approach to decision-making and learning under uncertainty. And we had a very quick overview of 3 of the key challenges that we face in reinforcement learning. The credit assignment problem of how to attribute consequences to previous states and actions. And we saw an example algorithm or an example approach of how to address this, for example, QLearning. We need to, in higher dimensional settings, understand how to interpret observations, and this is done using function approximation. We saw an example of doing this with the deep neural network or linear function approximator. And finally, we need to understand how to act given current knowledge. We saw a first approach to balancing exploration and exploitation in the form of epsilon greedy, and we'll look at more examples in just a second here. So let's look at the final piece of the puzzle, how to actually act in a situation where we need to balance exploration and exploitation. I'm starting this with two examples, and I want you to take a look and just think through what possible choices you might make in those situations. In the first one, you face a series of slot machines where someone told you that these slot machines might have different payoffs, but you don't know which ones those are and what kinds of payoffs they have. How would you decide which one to play next? What if I told you, like in this situation, that the current Q value estimates are like this? What kind of could you make use of that information? So we're in a different situation here. These are the Q values that the agent has already worked out. Given those, what action should I pick if I have 100 steps left to go?
I will try to. There are hundreds, so you can try either.
You can try any of them.
Yeah.
Mm-hmm.
I don't know if I should terminate, because like once you go into the lava, you terminate the experiment completely.
Mm-hmm. So that's a really good point here. So we assume that the experiment doesn't terminate completely. An assumption about the Markov decision processes that I didn't discuss was that the assumption is usually that the Markov decision processes we interact with are ergodic, which means that from any given point in time, we can reach any other state action pair in a finite number of steps. And so this means that we never have we assume that there is never a catastrophic failure. There is never a situation where the experiment ends and we don't get to continue. And this is an assumption we need to make in order for any of the approaches we know to actually work.
How would you model this in something like Minecraft, where basically you can actually die as a player?
Right. So it's modeled as an episodic setting. In an episodic setting, it's an alternative to discounting. So you can typically either assume that you have a continuous sequence of interactions and there's a discount factor smaller than 1, or you assume that there is a terminal state at some point at which you will typically break that series of iterates. You just update to the present terminal value, and this again allows you to have a finite. Basically, both of those make sure that your sequence of rewards is bounded in some way. All right, so after you have thought about this for a couple moments and developed some intuition of what the various choices are for balancing exploration and exploitation in those two settings, let's take a look at a few of the choices that people are commonly using in practice. A first very simple approach is something called optimistic initialization. And the principle of optimism is one that is often quite simple to implement in this particular form and can lead to very good behavior. Optimistic initialization in our earlier tabular example means that whenever we encounter a new state action pair, we assume initially that the value of that state action pair is high. And if we know, for example, that our rewards are bounded from above, then we can make a very informed choice of how to initialize state action pairs that we haven't yet encountered. This is, as mentioned, a simple approach. The only drawback is that it assumes that we have some estimate of the upper bound of the reward function. Even with such a simple approach, there's still quite interesting interactions between the initialization approach and the underlying optimization problem when we move to reinforcement learning with deep learning with function approximation. And this is one that we came across last year when we were looking at understanding exploration in deep reinforcement learning. We run experiments in a domain that is called the mountain car problem. This is a quite famous experimental setting in a reinforcement learning in the reinforcement learning literature, and it's modeled as this underpowered cart, which is kind of starts at the bottom of a valley, and it has to navigate all the way to this star here. the cart is underpowered, which means that it needs to go back and forth between those two hills up to the point where it has enough momentum to actually reach the target here. And this is often taken as an example of a hard exploration problem because the agent is assumed to not observe any positive reward until it reaches the goal position here. So it is something that requires strategic exploration. In our experiments, we found that depending on the function approximator use, we can learn, or an agent can learn this problem purely using optimistic initialization and no other exploration at all. But this behavior very much depended on the type of function approximator used. In the case where we used a linear function approximator, the agent would not encounter the target state. And this is represented here in the diagram that shows the coverage of the states the agent encounters during learning. We can see that those are all concentrated here near the middle of the plot, whereas the goal position is indicated by this red line over here. And so we can see that in the setting with linear function approximation, the agent never encounters the goal. If we keep everything as the same, but we use a deeper neural network function approximator, then depending on the architecture used, the agent is able to actually solve this task. It's able to do this the most efficiently when we use a 2 hidden layer neural network with ReLU activations. And we can see here that the agent learns very quickly. And in the way the kind of optimization of the neural network parameters works out, the agent is actually drawn to the states that give it high reward. And so this is one example that is not quite yet explained by what we know about deep reinforcement learning, but it's just an interesting example where we see that exploration exploitation together with deep function approximation and reinforcement learning has interesting interactions that can either hinder or help learning in those particular settings. Looking at a couple of other approaches to exploration exploitation that are common in the literature, this is the epsilon greedy strategy that we have already mentioned. In this setting, we take the current maximum value action with some probability 1 minus epsilon, and we distribute the remaining probability mass of epsilon on the remaining actions. So we can see that in our earlier example with probability epsilon, the agent would take this maximum action and it would distribute the remainder of its probability mass uniformly across those two actions. Based on this example, you can already see the advantages and drawbacks of this approach. An advantage is that the approach is easy to implement as long as we can easily derive the maximum action from our value function approximator, but we do not have any ability to learn additional information about the actions. And so, for example, catastrophic actions would be taken just as much as actions that are a very close second to the current maximum value action. Another popular alternative that is commonly used with a type of approach called policy gradient reinforcement learning is a so-called softmax policy. A softmax policy is a particular parameterization of the agent's policy in the form of a softmax function. And so we can interpret here the function h of SA as an action preference. So how much better do we estimate the action A to be than the other alternative actions in that particular state? This is exponentiated and then normalized in order to give us a probability distribution over actions for a given state. And so we can think of this as this transformation shown here at the bottom. This is really nice because the learned estimates, for example, if we think of these h's here as something that is highly correlated with our current Q value estimates, then we get a very natural way to trade off between actions that have high potential value versus those that have low value. There is typically a hyperparameter in the form of a temperature parameter that can be used to provide additional information into how steep that trade-off should be, how steep the decay should be between high value and low value actions. A fourth type of approach is an upper confidence bound type of approach, which models the uncertainty the agent has over its current value estimates. So if you imagine that in addition to the just expectations over the state action values that I showed you earlier, we instead had some estimate of our confidence, then the upper confidence bound type of approach would take the action that maximizes an upper bound. And so, for example, if there's a higher uncertainty on this action that has a slightly lower estimated value than the winning action, then this approach would take this action in order to learn more about the consequences of taking that action. This type of approach has very nice properties in theory and is guaranteed to converge very quickly if we are able to derive principled uncertainty estimates. And this is commonly possible in a simplification of the reinforcement learning setting called a banded approach, where there are no long-term consequences of actions in given states. But it's typically much harder to derive such principled estimates for the full reinforcement learning problem. And so while this approach has a lot of appeal conceptually, there's some key challenges that need to be addressed before this can practically be used in the full reinforcement learning setting. The final approach I want to highlight is called posterior sampling. And again, it relies on maintaining a distribution over state action values instead of just the expectations. Assume here that we have a model of the full posterior distribution over the state action value estimates. A posterior sampling approach would, at any given time step, take a draw from those posteriors, and then it would work out the optimal action given the draw from that distribution. So, for example, if you imagine sampling from this, and this function, then there's some probability that the values that we sampled for this action is higher than the one that we sampled for this. And this would give us some distribution over how we actually allocate our exploration budget in this particular setting. This concludes our discussion of exploration exploitation in reinforcement learning. So just to quickly recap, we addressed the problem of credit assignment function approximation and the problem of exploration and exploitation. When moving to deep reinforcement learning, we typically get a lot of interaction between those different components. So for example, we might get interactions between representation learning, so how the agent generalizes over different state action pairs, with either uncertainty estimation and exploration exploitation, and we saw one example of that. Another way in which these typically interact is in the stability of training. I already mentioned that under the hood in deep reinforcement learning, we ask the agent to solve a optimization problem that for all purposes kind of takes the form of a supervised learning problem. However, we are in a non-stationary setting where the data available to the agent continues to change. Finally, a key challenge is sample efficiency when actually learning the credit assignment. And there typically, when we have, when we require a large number of environment interactions, there are new interesting ways in which people make use of that data in order to speed up the optimization problem. Just to look at some examples of the key insights that were developed as part of the work on DQN, so the work where it was first shown that deep Q networks could be applied to learning a wide range of Atari games. This approach managed to stabilize Q learning in the function approximation setting with two key components. First of all, the authors stabilized deep neural network training by using what's called a replay buffer. So a large amount of previous environment agent interactions were stored in this replay buffer that was only slowly changed over time. And all the Q-learning updates were based on batched samples from that replay buffer. This stabilized training because now the data distribution would only change slowly and the rate at which it changed could be controlled. The second innovation there was that a target network was used in order to work out the Q value targets that were used when optimizing to minimize the temporal difference error. Again, this target network was only changed slowly over time, again, with the view of slowing down and stabilizing training in the setting of QLearning with function approximation. Right. I will be skipping the discussion of choosing state and actions and rewards, and I want to take about a 10-minute break. If you have any other questions on any of the material here, or if you want to discuss some more about how to choose state actions and rewards when applying reinforcement learning in practice, I'm happy to take that offline. Thanks so much for your attention so far. I think we can continue. As an example of decision-making under uncertainty, I'll make the uncertain decision to continue with the material I had for this first lecture. I think we'll have enough time, and we'll get through the material for the second lecture as well. And I did want to show you some of the material here. So let's take a look at what actually happens when we want to apply reinforcement learning to a new problem. There's some key design choices that the experimenter or practitioner needs to make. And this is in contrast to the frequent kind of perspective of a reinforcement learning researcher who often is handed a reinforcement learning problem that is already formulated in terms of state action spaces and reward function, and where their focus is to come up with new, for example, more sample efficient algorithms. When we apply RL in practice, we actually need to make those choices, and those choices have very important implications for how likely we will succeed in terms of finding an algorithm to effectively learn in those settings. So let's start with the state observation or state space. This is an important modeling choice because it essentially lets us formulate how we're representing the problem to the agent. We already saw two examples of this in the material so far. We saw a tabular representation in the form of a Q table where algorithms give us good guarantees, but where we run into the limitation that agents without function approximation may not be able to generalize over unseen state action pairs, and so they're stuck having to explore all possible state action pairs, which can be prohibitive if we are in a large environment with many states. We also saw the choice of looking at, for example, high-dimensional pixel observations, and that gives us the advantage that now we can use function approximation in order to generalize to new state action pairs. At the same time, we run into the problem that we're essentially using supervised learning under the hood, and now we need to deal with this complexity of trying to stabilize training in a setting where the underlying data and the underlying training targets are actually changing over time. In addition to that, we get an additional problem that the, for example, state action value may not be perfectly representable with the function approximator we chose. For example, if we use a very simple, let's say a linear function approximator, we may have to, the optimization under the hood may need to make trade-offs in terms of how accurately it can represent the various state action values. This can lead to aliasing, and that can also slow down or hinder learning in those settings. So whenever a practitioner makes a choice of how to formulate the problem, they need to take into consideration, for example, whether in their formulation, in their particular problem, the Markov property is satisfied, or maybe if they need to provide additional features that make the problem fully observable and allow them to use the machinery that we have discussed so far. They may want to make choices about how prior expert knowledge could be encoded. So, for example, they may make choices about what parts of the state space are actually visible or can be visited by the agent. And they need to ask themselves what the effects are on the optimal solution or on data efficiency. I won't have time to go into all of those in detail, and I just want to give a few thoughts based on previous literature in how the kind of choice of state observation space might work out. As already mentioned, the work on DQN, the demonstration of learning with function approximation from pixel images, was a very impressive result because it for the first time demonstrated that learning in a reinforcement learning setting with function approximation could stabilize enough in order to make use of learning with function approximation. And so the team under Mni et al. Impressively demonstrated that given enough data, such a deep QLearning algorithm was able to learn to play Atari games at or above human level. However, at the same time, the algorithm was very data inefficient. It required millions and millions of samples in order to achieve that very high level of performance. And so in this study that I really like, which was led by W in 2018, looked at what the difference is or might be between how humans interpret and play or learn to play video games and how an algorithm like DQN might learn to play those video games. The way they did this is they created a version of a video game, here a platformer game, that they manipulated in various ways in such a way that either human players or a DQN algorithm would observe the state of the game with a different type of observation. And they examined in detail how those different observations would affect learning ability of humans or DQN agents. And so this is a really nice way to look at what kinds of priors humans might use when they learn to play video games. This is an example of a playthrough by a human player in the vanilla version of the game. So you can see it's a platformer game. You need to collect keys, avoid or kill monsters, avoid spikes, etc. The first manipulation they used was to mask the semantics. So instead of having those pictograms as seen in the original version of the game under masked semantics, the kind of indication of what kind of object I might be dealing with was actually masked out in this situation. We can see by looking at the results that humans found it harder to play the game in this setting, whereas interestingly, a deep reinforcement learning agent was not affected by this manipulation at all. This gives us the insight that humans might use those semantic priors when they learn to play a new game, whereas deep reinforcement learning agents, for better or worse, aren't able to use such a prior, which slows down their learning in practice, but also doesn't hinder their learning when semantics aren't provided as part of the observation. As a next step, the authors masked out the identity of objects. So whereas here in the original game, we have gaps between monsters, so walkable area versus specific objects in the environment, the identity of objects here was masked out in the sense that all of them were replaced by colored blocks. Again, for human players, this made it much harder to learn to play the game, whereas deep QLearning agents were not affected at all. Again, this gives us interesting insights into why humans are so much more efficient when we learn to play video games in their kind of vanilla version. The most extreme manipulations that the team did were to mask out affordances. So there was no longer an indication of what might be objects, what you could interact with in this environment. And finally, they even masked out similarity. So while here you can still see that platforms have the same color, this similarity is completely removed in this most extreme treatment where similarity was masked out. As you can imagine, these are increasingly harder and harder to play by human players, but only one of those manipulations was actually affecting the learning ability of a deep QLearning agent. Do you want to guess which of those manipulations actually affected DQN? The last. Who says the last one? Who says C? Okay, you have the right intuition there. So D, exactly, mass similarity is affected. Why do you think that was the case?
Okay, so if they're trying to do it, they cannot say the state is similar to another. They were trying to do that because there's no similarities of the state.
Mm-hmm. Right. The intuition is that there's no similarity between the state. There's one more level of detail you can go into. DQN actually uses a deep Q network, which consists of convolutional layers and then fully connected layers. And convolutional layers are exactly encode a bias that essentially encodes visual similarity. And so here, the effectiveness of convolutional layers would be reduced, and the network would have to learn a lot more filters in order to capture similarity within that scene. really good insight. So moving on from the choice of state space to the choice of action space, again, the choice of action space is an important modeling choice, which can, for example, include the use of discrete actions. So, for example, whether a button is on or off, or which button to press, as is the case in Atari games. And we might be naturally in continuous domains. For example, in a robotics setting, this might include how much force to apply to what joint. And the kind of modeling of more kind of complex and more interesting action spaces is an ongoing and very interesting area of current reinforcement learning research. This includes, for example, action spaces that are very large or complex, combinatorial action spaces, spaces that mix, for example, discrete and continuous actions, and in the limit, as a very extreme example, the use of full natural language as an action space. Trade-offs of this choice include data efficiency. So you can imagine the larger your action space, the more actions the agent has to explore. So the more sample inefficient any algorithm is going to be. That is especially the case in continuous actions, where usually the agent has to, or kind of the decision of how to explore is a lot more complex. So typically continuous action spaces are more sample inefficient to learn. And the trade-offs here also include generalization. So for example, if the practitioner were to discretize a complex action space, then their choice of discretization can affect how effectively the algorithm can generalize over similar actions in that particular space. Just to give you one more example of how researchers are pushing the state of the art in reinforcement learning, here's an example of a platform for research where the researchers are trying to push research in using natural language as the action space for reinforcement learning. This is a research platform developed by people at Microsoft Research, including MSR Montreal. Based on this text world platform, they ran a competition last year to understand how effectively reinforcement learning agents are already able to make use of various ways of modeling natural language and generating and understanding full natural language. This takes the form here of text-based games, which is a really nice and interesting domain where a lot of tasks can be generated using the text world platform provided here. Insights that they have gained so far already are that a lot of the recent work on language modeling is really helping reinforcement learning agents. So while there is still a huge room for improvement here, researchers are starting to make progress in understanding how RL agents might be able to operate in a really text-based world. Finally, I wanted to briefly touch on this question of where the reward actually comes from. This is one of the most crucial modeling choices because the underlying kind of assumption so far has been that a practitioner is able to develop a good reward function for the agent to follow in such a way that maximizing reward, finding an optimal policy with respect to that reward function actually gives the experimenter the desired behavior policy. In some cases, there might be natural choices for this. So for example, in an Atari setting, the choice of game score might be a natural choice. But even there, we see that specific forms of, for example, normalizing that score can have really strong effects on how efficiently the algorithm is actually able to learn. Some of the challenges there include that it is hard to learn when the reward signal is very sparse. So for example, in a setting where the agent is able or needs to be able to achieve a given goal, it might be very natural to give the agent a positive reward when the goal is achieved. But waiting for the agent to accidentally come across that goal can take a very long time and can be very sample inefficient to learn. Another consideration is usability. So again, a practitioner needs to be able to formulate this reward function. So let's build some intuition on how strongly the choice of reward structure can actually affect a reinforcement learning agent. And to do this, let's look back at the example of a tabular QLearning agent learning the cliff walking task here within the Project Malmo Minecraft environment. Just to give you a quick reminder, earlier we saw that with the default reward structure that we provided here, the agent is able to learn this task very quickly. For example, after about 90 training episodes or just a few minutes of training, the agent is able to solve the task and obtain the diamond at the end of this, navigating this cliff. So now let's take a closer look at the reward structure that we actually used for learning here. There are three types of rewards that we're defining here as part of the Project Malmo task definition. First of all, if the agent encounters a block of lava, it gets a strong negative reward signal of -100, and this also terminates the episode. If it manages to find the diamond at the end of the platform, it gets a strong positive reward signal of +100, and again, this terminates the episode. And on all other steps, the agent gets a -1 step reward, which is designed to encourage the agent to find shorter and shorter paths as it learns to navigate this platform. But now what happens if we were to change this reward structure? So for example, over here, we have replaced the -100 negative reward for encountering lava with a -5 reward. And so you might think that's a pretty minor modification, and we have actually ensured that in principle, the optimal behavior is still the same behavior of actually navigating to the diamond as quickly as possible. But we can already see that this relatively small change in the reward structure has dramatic effects on learning the task. In contrast to the default reward structure, where the agent successfully learned the task within less than 100 training episodes, here, if we train the agent for 100 episodes, it is nowhere near solving the task, and it actually falls in lava very, very frequently. You can also see in the Q table that the agent has not yet covered the entire space and is still learning more about the different effects and consequences of its actions in this environment. A similar picture after 200 training episodes. Again, still the agent has nowhere near converged to the optimal behavior, and this continues after 300 episodes in this example. So we can see that even minor modifications like the one proposed here can have dramatic effects on how quickly an agent can actually learn a task. And as we move to more complex situations, for example, tasks where function approximation is required, picking the right reward structure can make the difference between getting an agent to learn this task successfully and entirely failing on learning that task. A lot of reinforcement learning expertise and experience are needed to construct these effective reward structures. And that is true even for those simple scenarios, but even more so in more complex applications. So we can see that as we try to move reinforcement learning towards more and more realistic real-world applications, constructing reward structures and debugging them can be a serious obstacle towards reaching those wider application areas. Just to give you a quick pointer, many promising ideas and research directions are currently being explored to address this challenge of creating ways to more easily defining or maybe automatically learning reward structures that can be used to successfully train agents to complete complex tasks. One project where we have recently addressed this challenge is the mineral competition. Following up on this idea of learning from demonstration, this research direction has inspired the Minorel competition that we have recently run at the NeurIPS conference. This competition is a close collaboration with a wide range of partners and led by William Guss at Carnegie Mellon University. The goal here is to provide an environment and a set of data that is able to facilitate and catalyze more research into sample-efficient reinforcement learning by building on knowledge that can be extracted from human demonstration. I want to conclude with a short video that gives an overview of this competition. The mineral competition has now concluded, and I would very much encourage you to check out the links I will show at the end of this lecture for details of the winners of the competition and the very exciting solutions towards more sample efficient, more generalizable reinforcement learning using human priors that these participants have developed. At the same time, challenges such as sample efficient learning, using human priors or demonstration data, and other questions about how to learn efficiently, for example, in more complex settings, including multi-agent scenarios, are wide open research questions. And I'm strongly convinced that we will see a lot of progress over those coming years, not in small part driven by more open-ended, more complex experimentation environments becoming available in combination with more and more data that can be used for actually driving innovation in this space. As part of this picture, Project Malmo is an open-ended experimentation platform that can support research progress on a wide range of experimentation scenarios and research directions, such as the ones mentioned previously. All right, results of this first competition will be made available at the NeurIPS conference. If you're interested in learning more about the competition, we will be including relevant resources and pointers with the webinar materials, so do follow up on those. Just to summarize, the mineral competition has a lot of demonstration data, and our goal here is to understand how to best leverage that demonstration data in order to achieve more sample-efficient reinforcement learning algorithms. I hope you have very much enjoyed the lecture today, and if you're eager to learn more or try some of the things that you have learned about today at home, here are some pointers to get you started. First, if you are watching this live, there will be the opportunity to participate in the live Q&A right after this webinar, and I'm very much looking forward to your questions. If you would like to learn more about reinforcement learning, one way to get into more advanced topics about this area are to check out my tutorial that is available in recorded form from the NeurIPS 2019 conference, and you can check that out online. If you would like to learn more about the exciting work that I am doing together with my team and other collaborators as part of the Microsoft Research Game Intelligence Group, I encourage you to check out our website where we have pointers to blog posts and some of our latest research articles. We used a lot of examples from Project Malmo today, and as mentioned, Project Malmo is a very general purpose experimentation platform that opens up the video game of Minecraft for constructing AI experiments, including a wide range of reinforcement learning experiments. If you would like to learn more, check out the links that are shown here on the slide. And last but not least, I gave you an overview of the mineral competition and how it is using an innovative experimentation setup to drive research towards sample-efficient, more generalizable reinforcement learning algorithms. While the competition has closed, the exciting results and insights that we obtained from participants are now provided on the website. So do check that out. Thank you so much for listening in today. Hi, everyone. Thank you so much for attending the seminar on exploring reinforcement learning methods from algorithm to applications and our live Q&A. I'm Katja Hofmann, and over the next 10 to 15 minutes, I'm going to answer some top questions that you have submitted today. Let's get started. Our first question is about what makes a problem formulation in reinforcement learning Markov, or alternatively, in what kind of settings we would see non-Markov formulations, for example, with partial observability. An easy way to imagine a problem where the Markov assumption does not hold because you have partial observability is if you imagine an agent that explores the world from a first-person perspective. So, for example, imagine a robot that has a mounted camera and needs to navigate through some hallway. It can only use its local observation, so it may not see what is behind the next door. It has to navigate to the space. It may require memory in order to maintain all the information about the environment that is necessary to solve the task. In many real-world applications, however, there might be choices that a practitioner can make in order to make a problem more fully observable. For example, in the hallway problem, it might be possible to include an overhead camera, and that might provide additional information that might make the problem more tractable. Another common example is in the benchmark that is posed by the Atari learning environment. There, if the agent needs to learn from pixel images, if only a single current pixel image is provided, then that might not give enough information, for example, to estimate the speed of moving objects. However, if the agent is provided with several frames at a time, which is called frame stacking, then the environment might be near fully observable, and the Markov assumption might hold approximately. So this is a really kind of nice way to think about when you are solving a real-world reinforcement learning problem, to really carefully think about how the observation space is defined, what kinds of assumptions can be made to hold or to hold approximately that might make learning easier in that setting. Another set of questions that came in, or that came up today a lot, is about changes over time. So, for example, what if we are in an MDP where the reward function or the transition function may change over time? In the most general setting, if we can make no additional assumptions about the problem, then this might be intractable. So, for example, if you imagine a setting where the reward function changes arbitrarily over time, there may not be enough structure for the agent to learn anything meaningful at all. However, in many real-world applications, we can make additional assumptions, and there are a lot of really interesting problem formulations that extend the MDP formulation to very specific non-stationary settings that can be very useful in practice. So if this is a type of problem that you're facing, then I encourage you to look at the literature to see what people have developed. One example formulation that makes very restrictive assumption and as a result might be very powerful is the base adaptive setting. So this assumes that an agent interacts with a class of MDPs that are related to each other through a very low dimensional piece of hidden information. And when the agent interacts with a given MDP, it can uncover information that allows it to make an inference about which task it's currently interacting with. And so this is a very powerful framework. It imposes a lot of additional structure in such a way that the agent can deal with the changes that it might experience over time very effectively. The next question that we've gotten is where do you see the set of next real-world applications of reinforcement learning? There are a set of real-world applications that I'm already very excited about are using a restricted formulation of reinforcement learning that is called a contextual banded setting. For example, the Azure Personalizer service is a product where this type of reinforcement learning is already used very effectively, for example, to personalize or adapt, for example, news websites to individual users. John Langford and Rafa Hosen drove a lot of that really exciting work, and they have a recent Microsoft Research podcast about this topic and the exciting research that is making this possible. So if you're interested in this type of application area, I encourage you to take a look and follow up with, for example, listening to this podcast. I strongly believe that in the longer term, reinforcement learning will completely revolutionize how we think about computers and how we interact with them. I believe that applications in video games are a really exciting application to test out that future, and this is why my team and I are so focused on using reinforcement learning to test out and develop new experiences within the video game space. So that's something I'm hugely excited about. We're starting to wrap up. The last question for today is going to be around research directions in reinforcement learning. So the question we have here is, what do you see as important research directions for reinforcement learning? My team and I are really motivated by developing reinforcement learning algorithms that are effective in practical real-world applications. So we really ask ourselves, and what are the problems, the fundamental problems that we need to solve in order to enable the next generation of reinforcement learning algorithms and reinforcement learning applications. And as mentioned, many of those we initially see in video game applications. One key limitation that is often hindering real-world applications today is sample efficiency. And some of our recent work in this space has been looking to improve sample efficiency of reinforcement learning algorithms, for example, by developing better abstractions, by exploring more effectively, and by developing algorithms that can generalize better to new subsets of reinforcement learning problems. We're also really interested in applications or in new algorithms for multi-agent reinforcement learning settings. In many real-world applications, a reinforcement learning agent will not act in some kind of vacuum, but it will interact with some human users, and their developing multi-agent approaches is really, really crucial. We believe that multi-agent reinforcement learning problems have some very interesting structure that can be exploited in order to develop effective and efficient algorithms for those challenging settings. And that's something that we're really pushing at the moment. With that, I want to thank you all for attending today. We really appreciate your participation, the interest, and the fantastic questions that you have sent on the subject. If you're interested in learning more, we have listed some great resources in the resource list to the right of your screen. This includes, for example, a pointer to my recent NeurIPS tutorial, and I would recommend this as a great way to follow up on this webinar because it goes in more detail on some aspects that we've touched on today and also discusses some of our latest research. If you are interested in the research that we're doing here at the Game Intelligence group in the Cambridge Lab, there are also pointers to our group as well as to some exciting blog posts about some of the research that we have published very recently. We look forward to seeing you build on this research and develop new insights in reinforcement learning, and in particular, we're looking to see some of those ideas applied in practice. With that, I wish you a great day.